Hello everyone and welcome to this C++ video on the unordered set header of the C++ standard library. In this video I'm gonna go over what an unordered set is, how it works, and how to enable an advanced feature called transparent lookup, which is gonna maximize the efficiency and the speed of the lookups. The first thing that I want to say is that this feature is available only from C++20 onwards for unordered containers. The same feature is available earlier for the ordered containers, for stdset and stdmap, but for an ordered container it's not available. The first thing you need to do is we open a new project and we include the unordered set header. An unordered set is a template container for elements which is associative, and it's like a menu of elements that are unique. Let's expand a bit on this. We can declare, for example, an unordered set of std string and call it available names. And we can put some names inside the set. We can put Simon, we can put Bob, we can put, of course, Alice. There's no Bob without Alice. We can put Mark, we can put Giovanni, and why not? Let's put espresso macchiato. So this set is gonna act as a menu of available names. This is just, well, a set. And what we can do is ask, for example, if a name is contained inside the set. What we can do is declare a bool found equals available names dot contains Giovanni. And of course I cannot type. There we go. This is gonna compile, and I want to show what it looks like in the debugger. So with this breakpoint, we initialize this set, and now it contains 6 items. And in this set, we can see the items, and if I do found, well, it says true because Giovanni is inside the set. But I want to highlight something about this set, something that you would not expect, and it's something about memory allocation. This is not efficient. To see this, I'm gonna hijack this new operator. This is something you should never do, except for debugging purposes. I'm gonna override the operator new. Size t, and it's gonna be no accept. Let's make it no accept false. And well, return std malloc n. This is basically what the new operator does, but I'm gonna add a line here to do std cout allocating and then n bytes of memory. This way we can see when an allocation is taking place inside our program. So let's run this again with this new overridden operator. When I run this line, you can see over here in the terminal that a bunch of allocations is taking place. This is basically copying all these items inside of the container and storing them, and also initializing probably some internal variables of the container. I really don't know, but you can see the allocations happening here. But look what happens when I run this line. If I run this line, you can see here in the terminal, boom, there's been an allocation. This is bad. We don't want to have an allocation when I'm looking for something. Why is there even an allocation in the first place? Well, the allocation happens because what we are passing in the containers method, this element is not an std string. It is a const car pointer. And you can tell me, but wait, we know how to compare a const car pointer to an std string. There are overridden operators for it. There's no need to do anything. What's going on? Well, the reason is the way the unordered set stores the items inside. So the way the items are stored inside the set is there is a hash function that computes the hash values of the elements inside the set. And based on that hash value, it stores them in separate buckets. You can imagine like different buckets labeled with different hash function values, and each item goes into that bucket. So if you have a very good hash function, all your items will be spread in different buckets. But if you have a very bad hash function, a lot of items will be in the same bucket. When we look for an item inside the set, we pass an element that has to be hashable because we want to hash what we're using to look for an item, and then use that value to identify the correct bucket, and then go into that bucket and look among those elements if there is one that is equal to what we pass through. So it's not directly comparing this element to the element of the set. It's gonna first compute the hash, then compare the hash values, and then compare the elements inside the bucket. This causes the search algorithms inside the set to run in constant time if your hash function is very good, because there's going to be just one element per bucket. But if your function is bad and all your elements end up in the same bucket, what happens is the algorithms are going to run in linear time, and this is bad. So the hash function is very important, but I mean, there are default hash functions for string. So what's happening here? Why is there the allocation? Well, the problem is this is not a string, it's a const car pointer, and there is not a hash for a const car pointer, so the set wants to be super safe. And what it's doing is it sees that it can convert this const car pointer to an std string. So it does that, and then it computes the hash of the std string and uses that hash to look inside the set. So this implicit conversion is why the memory is being allocated. But you will agree with me that this is completely unnecessary. What if there was a way to tell our set how to hash the values that we pass in, even if they are of different types, so that we can use them to be compared against the elements of the set? This feature exists in C++20 and it's called transparent lookup. What we need to do is to declare a custom hasher that tells our set how to compute the hash of all the elements that we want to be able to compare with what is in the set. Let's get coding and see how to do this. We need to declare a struct, which is a custom hasher. Custom hasher. And inside this struct, we need to provide the operators to compute the hash of the types we want to use to compare against the elements of our set. So if it's a set of strings, it's reasonable that we want to be able to look inside the set using strings or using string views or using a const car pointer without having to convert these two types to string. So what we have to do is declare the operators. How do we do that? Let's do it for the string first. One can do something like this: size t operator, and then do const std string reference str. This is of course const, no accept, and then inside here we can do return std hash of std string str. And this would work. This is using the hash function for std strings to compute the hash of this string. And you could think that it's just enough to add another hash function, for example, for a const char pointer. But this is a problem, because if I'm using the std string hash, this conversion is still gonna take place from here to here, because this const char pointer is gonna be hashed, getting converted into a string here. So we just move the problem in another spot. But you cannot even do this, because this would just hash the pointer value, like the address of the variable. It would not hash what the string is. So we need a common type, ideally, to which our types can be converted to at virtually no cost. And this type is the string view. So what I like to do is like declaring here using hasher, declaring what hasher we are using. As a hasher, we are using the std hash of std string view, because our types can be very easily converted to string view at no cost. And here, instead of using this hash, I'm just gonna use my hasher here. This is gonna convert the string to a string view, but this is not a problem. This doesn't cost anything, this conversion. Same here. The conversion to const char pointer to a string view is not an issue. And then, of course, we need to add the hash function for the string view itself. String view. So, this way, our set would know how to hash these different values, these different objects, using a common hasher. What we can do then is just to, wait, let me move this item in an initializer list. Std initializer list of type std string init list equals this, and then available name is just init list. Let me remove this. Wait, no, let's leave it here for a second. And now we can declare another set, std unordered set. We can build a set of std strings again, but this time we pass the custom hasher. And then we need to tell it also how to compare the values, because this is just telling the set how to hash them, but we need to tell them how to compare them. Well, we are very lucky in this case, because there already are comparison operators overloads for these types in the standard library. But so what we just need to do is use std equal to, and then put the empty angular brackets, are they called? I have no idea. And I'm gonna call this transparent set. And this transparent set, let's make it like so it's a bit more easy to read, is initialized with the same values. Okay, this is actually not enough, because this feature is not enabled by default. We need to manually enable by declaring this is transparent type equal to something. It doesn't matter. I just type void because it just needs to be defined. And this equal to with the empty bracket, it's a void specialization that is transparent. So this is enabling the transparent lookup for strings. I'm gonna do another example later where I'm gonna use a different type, and it's not gonna be strings. So let's now copy this line here, change the set, oops, and see what happens. I'm gonna run the program. It's not gonna compile because bfound is being redefined, of course. Tool found. There we go. Now it's compiling. So bunch of allocations for the set. Now, if I run this line, I'm expecting an allocation. There we go. If I run this line, I'm expecting an allocation because it's gonna initialize this set. And now if I run this line, boom, no allocation is taking place. What's happening is gonna not convert this const char pointer to a string. It's just gonna compute the hash value of that variable using the custom hasher that we provided. And this is a big deal. This really is a big deal, and I'm gonna show you why it's a big deal. Let's time what happens. Let's measure the performance. Let's not override this anymore, and let's include the chrono library. Chrono, there we go. Let's go here. Let's define a const exp size t iterations equals 1 million. This is 1 million, right? 1, 2, 3, 4, 5, 6. Yeah. Oh man. Oh man, I'm getting old. Then we do using L clock equals std chrono high resolution clock. There we go. And using ms equals std chrono milliseconds using no, never mind, no more usings. All right, let's do auto start time equals clock now, and then we set up the cycle for size t k equals 0, k less than iterations plus plus k. Very important to do plus plus k over k plus plus, because this doesn't allocate extra memory. And then we can do found equals, let's get this first, available names dot contains Alberto, which is false. And then here we can do auto end time equals clock now, and then we can do auto duration equals std chrono duration cast to milliseconds of end time minus start time dot count, and then we can do std cout time for iterations transparent lookups, sorry, no, just normal lookups, duration milliseconds slash new line. There we go. Oh man, sorry, I switched my keyboard to Italian. Okay, this should be okay. Now we do the same for the transparent lookup version. So this is not needed, this is not needed, this is not needed. Time for transparent lookup. All right, let's compile and execute and see what happens. Would you look at that? Yeah, I was expecting a much bigger difference, so I know there is something wrong, and what's wrong is that I did not change the set here. So let's just go transparent set. There we go. Let's compile it again and execute again. And all right, this is much more like, look at this enormous difference. For the normal lookup, it takes 1.2 seconds. For the transparent lookup, it's taking 162 milliseconds. This is enormous. And the bigger your keys are, the bigger your elements, the more that constructing that key is computationally heavy, the longer it takes. This is 10 times faster to do transparent lookups. So it's kind of a big deal. I want to before wrapping up the video, I want to show you something else. I'm going to show you how to use this transparent lookup to save memory when building associative containers. Let's suppose you are a pizzeria. Of course, you're a pizzeria, and you want to make a pizza menu. So, what's a pizza menu? Well, we declare a struct pizza, and a pizza has a name, and it also has a list of ingredients. This is what our pizza menus are like. So, std list of std string ingredients, and then of course the price, double price. There we go. And we can declare, for example, a couple pizzas here. Pizza margherita, which is just, well, of course it's margherita. Then it's a list of ingredients. It's gonna be pomodoro and mozzarella. And then the price is €6. Do I like that? Yeah. And then we can do another pizza, marinara. Marinara, which is marinara, which is pomodoro, aglio, and oregano. There we go. And then we can do pizza salamino, which is what non-Italians call pepperoni pizza, which is salamino, pomodoro, salamino, mozzarella. For example, let's change the prices. Like this is €5, this is €7. Yeah, more like it. And well, the menu is just an unordered set of pizza items, right? So we can compute std, an ordered set of pizzas. And we can call it menu and initialize it with these three pizzas: margherita, marinara, salamino. I'm gonna comment this for a second. Actually, no, I'm gonna show you that this does not compile. This is gonna give a compiler error, and the reason is that the set has no idea how to compute the hash of pizza. Well, I would say that's not a trivial question, right? How do you hash a pizza? Well, given the purpose of the menu, all we care about is the name, right? So we want to be able to look up for pizzas through their name, and we assume that the name identifies the pizza, so the name is kind of a label that is unique to this pizza. So for hashing the pizza, we actually just care about the name of the pizza. So we can do a pizza hasher, pizza hasher, and we can tell it how to compute the hash of a pizza. Const pizza, there we go, pizza. All right, well, I'm gonna use a string view as a hasher using hasher equals std string hash, of std string view. There we go. And then I'm going to enable the transparent lookup using is transparent equals void. There we go. And then I'm just going to do return hasher of pizza.name. So I'm going to compute the hash of the pizza just based on the name. And then I'm just going to also make 4 other hashers, because I want to be able to look for a pizza through its name. So I want to know how to hash a string. And then, wait, let me just copy these instead of these. I want to know how to hash a string view. Well, const car pointer and a string view. There we go. So, all these operators are not going to compile unless I mark them const, no except. Let's make this. There we go. But now we also need to tell the set how to compare the pizzas. If 2 pizzas are equal. So the hasher is not enough in this case, because there's no the computer doesn't know how to compare a pizza to a string. Well, and I'd argue that the computer is right. So we need to tell it struct pizza equals, and we need to define the operators to compare, for example, to pizza. Const pizza reference left hand side, const pizza reference right hand side, const no accept. There we go. And we can just do return left hand side dot name equals right hand side dot name. And then we need to supply the functions to compare the pizza to the other elements. So const std string, we need to be able to compare this to a pizza, and also the other way around. We want to be able to compare a pizza. Wait, what did I do? Oops. Const pizza to a const std string, and this is going to be left hand side dot name equals right hand side. There we go. And now we need to supply it for the next items, which is const car pointer. Oops, const car pointer here and const car pointer here, and then std string view here and std string view here. There we go. Now we supply this pizza hasher and pizza equals to this. We also need to enable the transparent lookup here, equals void. There we go. This should compile if I didn't make any mistakes. Let's go. Okay, it compiled and executed. And if I run this line, you can see that you have the 3 elements in here. And what I want to show you is that there is no allocation taking place. So I'm gonna decomment this override of these operators, and I'm gonna go down here and look for bool is there an abomination equals menu dot contains pineapple. There we go. Yeah, you can tell I'm Italian, right? So let's compile and execute. And well, there is a bunch of allocation taking place here and here, but what I want to show you is here, if I run this line, bam, no allocation takes place. So this way you can use the set to look for pizzas using their name. And you could argue, well, why not just use a map? And the reason you don't want to use a map is that you don't need to duplicate this memory. The name of the pizza is already here. If you do a map between a string and a pizza, you're basically taking up double the memory for the name because you need to have it in the key and also in the pizza. So if the ID of your object is already inside the object, you should use an unordered set and use that ID as a hasher and implement the transparent hasher and the transparent equals. If you're not working with C++20 and you are working with previous versions, all you need to do is, it's very similar. You don't need to supply a custom hasher and a custom equals. You need to supply a custom less struct that tells the set or the map how to order two elements. And well, this is it. This was my very first C++ video. I had to work with this transparent lookup feature for my job, and I found it very, very interesting, and I hope it was clear, and see you next time.